Hello everyone, welcome to this chapter, Compression and Consolidation of Soil. We are going to explain this chapter from 4 aspects. The first is compressibility of soil and fundamentals of consolidation. The second is one-dimensional consolidation test and interpretation. The third is calculation of settlement. The last one is time rate of consolidation. Now, let's start compressibility of soil and fundamentals of consolidation. Look at this figure, please. It's well recognized. When structural load is transmitted from its foundation to the ground soil, stress increase will be induced in the interior of the ground. The stress increase can lead to deformation of ground soil. So, applying structural loads is a common factor, leading to subsiding of the foundation and the structure. Except of structural load, there are many other factors which can lead to deformation of ground. For example, the water level dropped significantly. The burying stratum soil in foundation trench is disturbed due to construction impact. Subsidence is induced by vibration. Change in water content of some special soils may also cause deformation of ground. For instance, in loess ground, an increase in water content will result in additional subsidence of the structure, which is also called collapse settlement. Usually, settlement is the vertical displacement of ground due to compression of ground soil under structural loads. The load-induced soil deformations can be divided into volumetric deformation and deviatoric deformation. The volumetric deformation is mainly caused by the normal stress, which compacts the soil, resulting in soil contracting instead of soil failure. The deviatoric deformation is caused by the shear stress. When the shear stress is large enough, shear failure of the soil will be induced, and the soil deformation will develop continuously. Usually, shear failure over a large area is not allowed to happen in the ground. The foundation settlement discussed in this chapter focuses more on the volumetric deformation due to normal stresses. Foundation settlements are often large and potentially damaging to structures. Differential settlements cause a variety of problems for structures. When the structure or its foundation is stiff enough to prevent the distortion of the structure, uneven settlement causes tilt. In fact, the internal factor causing the load-induced soil deformation is the three-phases components of soil. The soil is composed of solid particle, liquid water, and air. After applying the load, soil is compressed. The reasons for the reducing in soil volume due to loading are on the following 4 aspects: compression of solid particles, compression of water, expulsion of air, the partial drainage of pore water. It has been found, regarding to the pressure range, about 100 to 600 kilopascal, normally encountered in the engineering practice, the compression of the soil particles and the pore water is very small. Therefore, they can be omitted. Currently, the soil volume compression is thought of as the result of the expulsion of pore air and the partial drainage of pore water. Obviously, for a saturated soil, soil volume compression is mainly due to discharge of some pore water. The soil is compressed due to partial discharge of the pore water and pore air under structural loads. Usually, the characteristics of volume decrease in soil when subjected to pressure is called compressibility. Obviously, the discharge of the pore water and pore air needs a length of time to complete. Such a time-related compression process is called consolidation. The consolidation process of saturated soils is in effect a process of discharge of the pore water and the corresponding increase in the density. Generally, the coarse-grained soils, such as sands and gravels, have high permeability, consolidate at a much faster rate, and produce smaller settlement. Hence, the consolidation process completes in a short length of time. On the contrary, the fine-grained soils, such as silts and clays, have low permeability, consolidate at a low rate, and produce large sediment. Hence, the consolidation process completes in a long length of time. What's the difference between compaction and consolidation? It's well known, compaction is the process of increasing the density of soil by packing the particles closer together with a reduction in the volume of air. The volume of water remains unchanged. For the saturated soil, consolidation is a time-related process of increasing the density of soil by drawing some water out of the voids. We have known consolidation is a time-related process. Then, let's discuss fundamentals of consolidation. When a saturated soil layer is subjected to a stress increase, the pore water pressure is increased suddenly. Pore water drainage is accompanied by a reduction in the volume of the soil mass, which results in settlement. In sandy soils that are highly permeable, the drainage caused by the increase in the pore water pressure is complete immediately. When a saturated compressible clay layer is subjected to a stress increase, because the hydraulic conductivity of clay is significantly smaller than that of sand, the excess pore water pressure generated by loading gradually dissipates over a long period. The time-dependent deformation of saturated clay soil best can be understood by considering a simple model that consists of a cylinder with a spring at its center. The cylinder is filled with water and has a frictionless piston with a valve. The cylinder itself simulates the conditions of no lateral strain in the soil. The spring represents the compressible soil skeleton, the water in the cylinder representing the pore water, and the piston with valve representing the drainage condition. At this time, if we place a load P on the piston and keep the valve closed, the entire load will be taken by the water in the cylinder, because water is incompressible. The pore water pressure increase delta U equal to total stress increase delta sigma. The spring will not go through any deformation. Therefore, the effective stress increase delta sigma prime is 0. This situation with valve closed corresponding to the undrained condition in the soil. Now, if the valve is opened, the water will flow outward. This flow will be accompanied by a reduction of the excess pore water pressure and an increase in the compression of the spring. At any time, the effective stress increase on the spring equals to the reduction in pressure in the water. After some time, eventually, the excess pore water pressure delta U will become 0. The entire load will be taken by the spring, and the system will reach a state of equilibrium. Now, let's consider a saturated clay layer with top and bottom drain. A layer of saturated clay of thickness H is confined between two layers of sand and is subjected to an instantaneous increase in total stress. Since clay has very low hydraulic conductivity and water is incompressible compared with the soil skeleton, and time t equals to 0, the total stress increase will be carried by water at all depths. None will be carried by the soil skeleton. After the application of total stress increase to the clay layer, the water in the void space will begin to be squeezed out and will drain both directions into the sand layers. By this process, the excess pore water pressure at any depth on the clay layer will gradually decrease, and the stress carried by the solid particles will increase. However, the magnitudes of effective stress increase and the pore water pressure increase and various depths will change depending on the minimum distance of the drainage path to either the top or bottom sand layer. Theoretically, at time t equals to infinity, the entire excess pore water pressure will dissipate by drainage from all points of the clay. Then the total stress increase would be carried by the soil structure. This gradual process of drainage under additional load application and the associated transfer of excess water pressure to effective stress cause the time-dependent settlement in the clay soil layer. It's not uncommon for settlements as large as several feet to occur as a result of compression of soft layers. The following two stability conditions must be satisfied for designing a foundation. The foundation must not collapse or become unstable under any conceivable loading. This is called ultimate limit state. The other condition is settlement of the structure must be within tolerable limits so as not to impair the design function of the structure. This is called serviceability limit state. It's easy to understand. Estimating the magnitudes and the rates of foundation settlement in advance are very important. Appropriate design features can be adopted to reduce settlements or avoid settlement-induced damage. To do this, it's useful to be able to estimate how much will the cell set up on loading and how long will it take to finish. A summary: settlement occurs when the ground soil is compressed. Soil volume compression is mainly due to drainage of some pore water. Consolidation is a time-related process of transferring excess pore water pressure to effective stress. Compression and consolidation are important to the settlement determination. Thank you for watching.